In this video, we will explore some of the features of BESA's connectivity workflow in more detail, and how they can be used to find information treasures that are hidden in the data. We have a data set with two conditions, based on correct and erroneous answers to a visual task. I have computed time frequency using two methods, complex demodulation and Morley wavelets. Let me start the connectivity analysis. I will check out coherence, imaginary part of coherency, Granger causality, and partial directed coherence. Now go with the correct project. The file info shows that I have 11 source montage channels. I will keep the regularization settings unchanged and plunge straight into connectivity analysis. Now this takes a little while, with two conditions, two different time frequency methods, and 4 connectivity methods. But here we are. This checkbox shows me that we're looking at the correct answers here. First of all, let me hide the diagonal, which is just the self-spectrum. One issue that is typical for coherence is that for source montages, there may be a common noise modeling in different sources, which shows as a large coherence value between neighboring sources. So let's go to imaginary part of coherency and switch to wavelets. I'm going to scale up a bit. And also improve the display for checking out the matrix. Switch off the information window at the bottom and zoom the whole display. The VIR and MCR sources show some coupling here. Let me look at this in 3D mode. Now I can see a really interesting network spanning the visual areas. The right motor cortex, used for pressing the left button, and the right temporal lobe. Also, it is interesting that the lateral visual areas drive the motor cortex here. If I go through the latencies, I can see how the connection starts at about 100 milliseconds after stimulus, then increasingly involves more sources, and goes off again at about 400 milliseconds. I want to record a video for this. I will go from approximately 60 milliseconds to 380 milliseconds. The duration per latency step is, say, 0.2. And let's add a rotation so we can see the third dimension better in the video. But 30 degrees should be enough. Going to and from. Once it is complete, I can save it to file. Let us just have a quick look at it with the Windows video player. We can see how the latency runs through the time points and how the network adjusts. Let me go back to the matrix plot now. And I would like to compare the network with the one that I can find in partial directed coherence mode. This is a method that exploits the mathematical formalism of Granger causality. I first scale up to 2.0. If I look for clear peaks in the plot, I can see a connection again in the right hemispheric central posterior part. How does it actually compare with the error response? It seems less pronounced here. But how about the low-frequency connection to the cingulus? Start the 3D mode again, and I see the strong connection. I can also directly compare the network in the two conditions in the 3D plot. It may make sense to average over the time segment where this processing takes place, especially in this case of late responses. Let me average over time from around 300 milliseconds to 450 milliseconds. Now I can see the peaks at the left side of the detail windows. And I go down to the largest peak at around 3 Hz and directly see the network. It emerges that the network for the correct response is more complex than in any case of erroneous responses. I can export these results as connectivity data to ASCII files to import later into MATLAB or other packages. Now let me finish this project and save so I can reload the results at any point in time later. This concludes this video session, where we explored different time-frequency methods applied to several connectivity methods for 2 different conditions all in one go. Thank you.